Scientists say data from the spacecraft, named Ebb and Flow,
Ebb and Flow have removed a veil from the moon.
The moon isn't dead. It breathes.
The next few hours for the probes will be critical. Both spacecraft have to get into position low over the moon's surface.
Earth's gravity needs it each orbit, lifting rock like invisible tides. NASA scientist Ryan Park and his team uncovered this hidden heartbeat, proof the moon is more alive than we imagined, reshaping how we land, where we build, and what a world can be. The flexing moon. Ryan Park watched as two washing machine-sized probes, Ebb and Flow, chased each other around the moon. For a year, they whispered distances thinner than a human hair. When the data came back, Park expected a static rock. Instead, he saw a living response, stone bending under Earth's pull. Park later remembered that it wasn't supposed to move that way. Yet every time they checked, the flex was still there. Except it wasn't the same everywhere. The Earth-facing hemisphere bent more than the far side. Imagine a stress ball. One half warm and pliable, the other cold and stiff. Squeeze. One side yields first. If the moon were uniform, that asymmetry wouldn't exist. It does. Something beneath the near side is still warm, still different. The team reran solutions for years with different assumptions and tide models. The asymmetry persisted. Cross-checks against independent deformation theory held. Skeptics asked if it was a processing ghost. The data said no. The moon moves like a living thing under steady hands you cannot touch. For the Apollo crews, the moon felt like a silent, lifeless rock. But decades later, Ryan Park's data revealed that under their very boots, it was shifting, flexing in rhythm with Earth's pull, alive in ways they could never imagine. That strange flexing wasn't random. It connected to a mystery we've stared at for centuries. Why the moon shows two faces, one familiar and one alien. The moon's two faces. We have always seen the split on the surface. The near side shows vast dark Maria, ancient seas of lava, covering roughly a third of the face we know. The far side is fortress country, thicker crust, bright highlands, and craters stacked on craters, with almost no Maria. Theories piled up, more impacts on one side, a far side crust too thick for magma to punch through, Earth's gravity focusing heat toward us. None of it fully clicked. Grail's flex map adds the missing dimension, mechanics. The near side moves more because it's warmer and softer at depth. The far side resists because it's colder and stiffer. Whatever sculpted two very different surfaces also baked two different sets of bones inside. Deep beneath the familiar face, heat-making elements, uranium, thorium, potassium, are concentrated in a buried province. Over billions of years, their slow radioactive decay behaved like an internal space heater, keeping parts of the mantle supple. That's why lava once welled up to paint the Maria, and why the near side still yields more to Earth's pull today. Every orbit, the warm half deforms extra. Grail reads the difference like a signature. Think about what that means. The moon's interior didn't cool evenly. From a catastrophic impact, debris coalesced into a body whose chemistry pooled lopsidedly. Heavy, heat-producing elements didn't distribute at random. They gathered preferentially beneath the hemisphere that faces Earth. The result is a built-in furnace that never fully went out. A quiet heater that still modulates how rock flows and flexes. On the surface, the consequences are written in basalt and brightness. On the inside, they're written in mechanics. A softer near side mantle, a stiffer far side shell, stress fields that load and release on a schedule set by gravity. The moon is two-faced not only to our eyes, but to the tides that need it. But surface contrasts weren't enough. To know why one side bends and the other resists, Park's team had to peel back the crust and look inside. An X-ray of the moon. X-raying the moon. This was one of the most precise gravity experiments ever flown. Ebb and Flow orbited so low they had to dodge mountains. Solar pressure nudged them. Thermal gradients whispered. The gravity of Earth, the Sun, and even distant planets tugged. Engineers modeled every nudge, every hiss, then subtracted it, leaving only the moon's pull. What remained was an atlas sharp enough to feel hidden mass beneath crater floors and lava seas. And then something new. Time. Not just where mass sits, but how the whole body flexes as tides pass through it. That temporal signal cracked the interior open like an MRI. The instruments could sense gravity variations caused by features as small as individual mountains and subsurface structures invisible from the surface, and then watch the field change as the moon deformed under Earth's pull. To keep that signal honest, the team attacked the data from every angle. They switched tide models. They altered thermal assumptions. They reprocessed the tracking with alternate filters. They ran the problem millions of times. If the asymmetry were a mirage, it would collapse under the weight of those tests. It didn't. The same near-side extra flexing reappeared, locked to the orbit like clockwork. Precision at this scale is hard to imagine. Picture measuring a car's speed by detecting changes smaller than the thickness of paint on its surface. Now, do it from lunar orbit, while everything in the solar system leans on your spacecraft. That is the level of care required to isolate the moon's whisper from the cosmic noise. And yet, when you strip away the noise, the story is simple. Gravity is a storyteller. Give it the right instruments, and it reads you a diary of rock moving in the dark. These discoveries across the solar system rewrote our understanding of planetary interiors. But, for us, the most urgent implications return to the moon, because it's not just a laboratory, it's our next home. Other worlds reveal. Once you have the tool, you point it everywhere. On the asteroid Vesta, gravity and wobble suggest a surprisingly uniform interior, more rubble pile relic than tidy layered planetesimal. It's as if a violent pass shattered any neat structure and left a body reassembled from fragments. On Jupiter's moon, Io, the most volcanic place we know, flybys imply not a single global magma ocean, but scattered magma pockets embedded in hot rock, fed by tides that squeeze and shear every orbit. That's a warning against simple models. Even under brutal tidal heating, interiors can be patchwork, not pools. Icy moons like Enceladus and Europa advertise hidden oceans through gravity, wobble, and geysers that needle through their ice shells. The details differ, but the pattern is clear. Interiors are messier, patchier, and more alive than the diagrams in old textbooks. Mechanics, not just chemistry, sets the stage for where heat lives, where cracks open, and where energy flows. These findings ripple outward to thousands of exoplanets. If a simple airless moon can end up two-faced, then distant worlds likely carry stranger lopsided bones. Asymmetry changes everything. How magnetic fields arise, when volcanoes erupt, whether atmospheres persist, where liquid water can linger. Planets don't have to be tidy to be alive. They can be patchwork, and that patchwork can determine where chemistry runs long enough to matter. It also reshapes our origin stories. Early planetary formation was not a gentle snowfall of dust, but a brawl, catastrophic impacts, molten oceans, and debris rings sculpted by gravity's rough hands. In that chaos, materials segregated in ways our older models simplified away. The moon's near-side heater is a fossil of that chaos, still influencing tides and quakes billions of years later. Why it matters for us. This isn't trivia, it's a flight manual. When you try to land within meters of a resource or a science target, gravity is your wind. The Grail Atlas, and its tidal update, lets navigators thread approaches that don't drift miles off target. A tiny unseen hill of dense rock can tug a spacecraft enough to push a landing ellipse into bad ground. A precise map flattens those surprises and trims propellant budgets. Then there are moonquakes. Tides don't just bend rock, they stress faults. Boundary zones between the flexy near side and the rigid far side may host more creaks and snaps. Habitat designers will choose sites, foundations, and anchoring with those stress lines in mind, the way skyscrapers are tuned for wind. Dust behavior, regolith stability, and the risk of slow slumping on slopes are all tied to the local stress regime. Opportunity hides there too. Warmer crust may shape permafrost stability, the accessibility of buried volatiles, even thermal strategies for the brutal 2-week lunar night. A site with a slightly higher internal heat flow might ease power and thermal loads on habitats. A stiffer, colder region might offer seismic quiet. Either way, the where of the moon's interior becomes part of the how of living there. Here's the simple loop. Radioactive decay warms the rock. Warmer rock flexes more under Earth's tides. That flexing creates frictional heat. The added heat keeps the rock warm. It's not a runaway reaction, it's steady and persistent. Over geologic time, it kept the near side mechanically different. With long-lived seismometers and orbiters, we'll watch the moon evolve in slow motion, detecting year-to-year changes in gravity, a planetary pulse and blood pressure. That steady pulse may be faint, but it means the moon is still working, still storing memory. And that changes how we see it, not as a dead rock, but as something alive. The moon isn't dead. It breathes under Earth's pull, remembers the fire of its birth, and flexes with every orbit. By that measure, it is alive. When the next footprints land, they won't touch a silent rock, but a world with a living pulse.